Okay, welcome everyone to the string seminar. Today we are happy to have João Rodrigues, um, and he'll talk about exact solutions of matrix models and string theory. Over to you, Joe.
All right, so hello everyone. I would like to start by thanking the organizers, and in particular Professor Mahajan, for inviting me to present my work here today. It's a great pleasure to do so. So today I want to present to you a bit the work that I've developed over the last 3 years of my PhD program. So this work is based on a trilogy of forthcoming papers with my advisor, Ricardo Schiappa, back in Lisbon. Jasper Kager and Noam Tamarin, two PhD students in my research group, and Max Schwick, a postdoc in Bern. And also towards the end of the talk, I'll be saying some things associated with another forthcoming paper with David Berenstein from Santa Barbara and Victor Rodrigues from a postdoc in Santa Barbara as well. All right, so as the title of this talk claims, I'll be building exact solutions for a rather broad class of matrix models and their corresponding string theories by resorting to resurgence theory. Okay, so let me start by giving away the punchline of the talk in hopes of sparking your curiosity for what is to come. So the story starts with your typical genus expansion of Hermitian 1 matrix models. So these are the models that we're going to focus upon on this talk. And so it is well known that these expansions are asymptotic in nature, and thus, in order to and so they cannot be trusted to yield sensible results. And to fix this issue, resurgence instructs us to complement them with many more asymptotic series, making up the object known as a transseries. Now, many of the asymptotic series featuring in the transseries, they come attached with exponentially suppressed terms, like the one I've highlighted here in blue, and those should often be interpreted as, from the worldsheet point of view, as arising from deep-brain contributions to the gravitational path integral. Now, the novelty here lies in the fact that the transseries also features many asymptotic series that come attached with exponentially enhanced terms, such as the one that I've highlighted here in orange, and those should be interpreted from the worldsheet point of view or as arising from negative tension deep-brain contributions to the path integral. Now, interestingly enough, it is the added effect of both negative and positive tension deep-brains reflected on the transseries structure that conspires to promote our original asymptotic genus expansion into a fully exact, and more importantly, background independent solution of the matrix model and the corresponding string theory. Okay, so this really is the take-home message of the talk. Now, before I go into more detail regarding what these things mean, I'll start by providing a very brief overview. So I will be I'll be starting by giving you a very compact introduction to summability and resurgence, after which I'll provide a very short resurgent overview on matrix models that I will need in order to build the exact solutions that I was talking about just now. Then I'll try to convince you that these exact solutions are the real deal by showing you some very cool numerical consistency checks that we have done. And finally, I'll wrap up the presentation by, if time permits, by showing you some very small first steps that we have taken regarding generalizing this story to unitary matrix models. Okay, so that's roughly how the presentation will go. So now let me start by a second. Okay, let me start by the introduction to summability and resurgence. So as you might expect, the story starts with the generic asymptotic series, which I've denoted here by phi of z. So here I don't take any series. I ask that its coefficients grow at most factorially. And this leads to a rather broad class of asymptotic series that in particular contains most examples of physical interest. So it's not really too heavy of a restriction from a physical point of view. And this broad class of asymptotic series has a very natural resummation procedure called the Borel summation procedure, which whose first step consists in applying a Borel transform to our series, which I've denoted here by this curly b. So you can think of the Borel transform as a map that maps our series into a new series whose coefficients have had their factorial growth modeled out. Okay. So the resulting object, denoted here by curly b, of phi of a new variable that I call s, is now by definition a converging power series in the complex S-plane, meaning that it has a finite non-zero radius of convergence. So now, before I go on with the generic Borel summation procedure, let me try to follow along with a rather simple but pedagogical example where I'll illustrate these steps carefully. So I've chosen here the Euler ordinary differential equation, which I've written here. So we can plug a perturbative series ansatz into this differential equation and recursively solving for its coefficients. And if we do this, we obtain the series that I've written here. And it's not too hard to see that this series is actually asymptotic, precisely because its coefficients have a very explicit factorial growth. So what we can do is apply the Borel transform, and doing so yields the power series that I've written here, which you can clearly see is convergent, meaning that it has a finite radius of convergence. Okay, so but this is just really an example. Now we can go back to the generic procedure of the Borel summation. Okay, and so the next step consists in performing the analytical extension of our converging power series into the complex S-plane, thus obtaining a meromorphic and often multi-valued function that I've denoted here by capital phi of S. If we go back to the Euler equation example, performing this step is very trivial as it only requires using the geometric sum formula, which is exactly what we did here, yielding in the end, indeed, a meromorphic function in the complex S-plane, which, by the way, in this context, we call it the Borel plane for obvious reasons. And indeed, the function has a single simple pole on the Borel plane, which I have highlighted here by this green disk. Now, the Borel plane is a rather interesting region, and that is a neighborhood of the positive real line, which I've shaded here in purple. And the reason for this lies in the next and final step of our Borel summation procedure. So the final step requires performing the Laplace transform, which I've denoted here by a curly L, of the analytical extension of our Borel transform. And so it depends rather crucially in understanding our analytical extension in the positive real line. Okay, so the reason why we use the Laplace transform here, it's precisely because term-wise, in our original asymptotic series, the Laplace transform is the formal inverse map of the Borel transform, okay? And so, in the end of the day, it is a function that is locally holomorphic, but most importantly, asymptotic to the series that we've started with. Okay, so this essentially wraps up the Borel summation procedure, which I've chosen to denote here by a curly S, as indeed we obtain what we were looking for, namely a function that is well defined, at least locally, but most importantly, it's asymptotic to the series that we started with. So if we actually go back once again to our Euler equation example, this last step can be performed exactly. Namely, we can actually compute the Laplace transform, and doing so yields the exponential integral function that I've written here. And indeed, it's not too hard to check that this function is a particular solution of the Euler ODE that we started with. So the Borel summation procedure is indeed a very consistent one. Now, there's one rather intriguing question left to ask, and that is, what about the singularity that we found on the Borel plane previously? Is there something interesting going on there? And perhaps more importantly, does it encode information that can be useful to us? And so lurking in the answer to this question lies the need to develop a better understanding of the behavior of our Borel summation procedure under analytical extension. And fortunately for us, resurgence theory is precisely the framework that allows us to do this. So if we freely analytically extend our Borel summation procedure in the x-plane, in the complex x-plane, so here x is just 1 over z, it's what we call our recursion variable, then we really do need to watch out for convergence of the integral associated with the Laplace transform, because if we move around in the complex x-plane, eventually we may reach a point at which we lose convergence of the integral, and thus the analytical extension breaks down. So the recipe to build a good and sustainable analytical extension of our Borel summation procedure consists in continuously varying the angle of our Laplace transform integral contour as we vary the phase of x by essentially keeping them the same, as this will ensure that the argument of the exponential sitting in the integrand of the Laplace transform will be constantly negative. Okay, and so the integrand will be constantly exponentially suppressed, and this will ensure convergence of the integrand. Okay, so that's the idea behind the analytical extension. And this is precisely what I tried to convey with this picture here, where on the right-hand side, you can see that as I vary the phase of x along the dark red analytical extension line in the complex x-plane, I simultaneously need to vary the angle of the Laplace transform integration contour back on the Borel plane here, which I've denoted by this brown line. Now you can see that there's something very interesting happening when our analytical extension path crosses the negative real line, which I've highlighted here in blue, and in this context is called the Stokes line. And indeed, this is precisely the point at which, back in the Borel plane, our Laplace transform integration contour clashes with the only singularity in the Borel plane. And this clash essentially yields an extra integral of our Borel transform over a contour that wraps the singularity, okay, which I've denoted here by gamma. Well, this integral is generally non-zero, and so for all purposes, it is a discontinuity of our Borel summation procedure naive analytical extension, okay? And in order to fix this, we need to redefine the solution that we're building by using the Borel summation upon crossing the Stokes lines by actively subtracting the discontinuity that we just obtained. Okay, but this is something we can do easily, for example, by defining the function by branches. And doing so, we can happily keep following our analytical extension path to the place that we started, only to realize that the discontinuity that we are forced to subtract to ensure analyticity in the Stokes line, which I've written here, is exactly the monodromy of the Borel summation function. Okay, so this is all very consistent. Now, there's actually one remark that is very important to make here, and that is the fact that the discontinuity that we were forced to subtract, which I've written here, is actually non-analytic at z equals infinity, precisely because of the presence of this exponential term that I've highlighted in purple, okay? And so, for all purposes, this discontinuity is actually a non-perturbative contribution. And this leads to the main punchline of this section, which is that resurgence theory seems to indicate that in order to globally make sense of the Borel summation of an asymptotic series, and here by globally I really mean in order to be able to go beyond Stokes lines, then we need to account for possible non-perturbative contributions that arise from these obstructions in the Borel plane. Okay? So this is a very important lesson, and from it, we think that it would be very good to have an object that already encodes all such possible non-perturbative discontinuities. And this object is precisely the transseries. So let me try to define transseries in the simplest case, in which our Borel transform only has one singularity, such as the example of the other equation. So the transseries will generically look like this. So it has two terms. The first term we call the perturbative sector, and this is precisely the asymptotic series that we started with. And the second term we call the non-perturbative transseries sector, and this is another asymptotic series that multiplies an exponential non-analytic term such as the one we just uncovered in the previous slide, which we typically call a transmonomial. And it also multiplies a free parameter, which we denote here and henceforth by sigma, that we call the transseries parameter. If we go back once again to the other equation example, the transseries takes a very simple shape. Essentially, it's given here by this expression, where, as you may recall, this first term, the perturbative sector, is precisely the asymptotic series we got by plugging the series ansatz into the equation and recursively solving for the coefficients. And the second term here is the non-perturbative transseries sector, which in this particular case is actually trivial, because the asymptotic series only has one non-zero element, which is equal to 1. So it's very worth pointing out that upon Borel summation, this transseries actually exhausts all solutions of the Euler equation. And that is precisely because, as you may recall, the Borel summation of this perturbative sector yields the exponential integral function, which we saw was a particular solution of the Euler ODE. And the second term here already by itself is a one-parameter family of solutions to the associated homogeneous equation. Okay, and so because we're looking at the first-order differential equation, the Borel summation indeed does exhaust all solutions. And this is actually a feature that repeats itself in resurgence precisely because the transseries parameters, so these sigmas, are always to be interpreted as the integration constants associated with the differential equation we're trying to solve. Okay, so this really is one of the main advantages of working with transseries, which is that essentially we can work with all solutions at once. All right, so now let me try to generalize this story a bit to include cases in which you can have multiple.
Hi, hello.
Yeah. Hello.
In cases where you're not solving a differential equation, but some general problem where you end up with an asymptotic series and you
Yes.
do this procedure of reinterpreting it as some trans series, how do you interpret the sigma parameters there? Because you don't really have a differential equation with some integration constants.
Yeah, that's true. And so in these cases, so you know that whenever you have a perturbative solution to a problem, there is always a non-perturbative ambiguity associated in how you want to complete it. These transseries parameters reflect the degrees of freedom on that non-perturbative ambiguity. So if the problem is solved by differential equation, then this is explicitly manifested in the integration constants. But in more generic problems, it's precisely that non-perturbative ambiguity that has to be solved by extra physical input.
Okay.
Yeah. So, all right. So now we want to consider problems in which we can have multiple singularities in the Borel plane. So to accommodate for these problems, we need to upgrade our notion of transseries to include multiple non-perturbative transseries sectors, one for each singularity, precisely because each singularity can now pose as an obstruction to the analytical extension of the Borel summation. So in the example I've chosen here, I chose 3 singularities, this time branch points and not really simple poles, because this is the most common kind of singularity that you can have in physical problems. And because we have 3, our transseries will need to have 3 non-perturbative sectors. So eventually you get something like this, where the first term that you see here is our perturbative sector, so our original asymptotic series. And the second term iterates over our 3 non-perturbative sectors, which I've denoted here by psi I. Okay, so each psi I in itself is an asymptotic series that multiplies its respective transmonomial and its respective transseries parameter. Now, much like in the Euler equation example, we are going to get a non-perturbative discontinuity upon analytical expansion given by the integral of the Borel transform over a contour that wraps now not only the singularity, but also the branch cut that emanates from it. Okay, and one such example is denoted here by gamma 1. Now, interestingly enough, if we actually perform the integral over this contour, we get not just a single term like we had before, but actually exactly the Borel summation of one of our non-perturbative transseries sectors, which in this case happened to be psi1, multiplied by the respective transmonomial and a complex constant, which we call the Stokes constant. So here it's worth making a brief aside, and this is that in physical settings, generally, these non-perturbative transseries sectors that arise from these obstructions can alternatively be obtained by expanding our path integral around instanton configurations, okay? In which case, the argument of the transmonomial, which I've denoted here by this A1, is precisely the instanton action associated with the configuration, okay? And for this very reason, from now on, we'll refer to the arguments of the transmonomials as instanton actions. Okay, but this is more terminology than anything else. So back in the complex X plane, now each singularity will result in a Stokes line. So now we have 3 Stokes line. And now, by resorting to the transseries, it's actually very easy and convenient to perform the good and unique analytical extension of our Borel summation upon crossing a Stokes lines by simply appropriately shifting the transseries parameters according to the Stokes constants in such a way as to cancel the discontinuity that arises from the obstruction in the Borel plane. Okay, and that's precisely what I tried to convey with this picture here, by assigning different transseries parameter configurations to the different regions bounded by Stokes lines. So this is another very good advantage of working with the transseries, is that it makes analytical extension very easy. All right, so I want to just do one more generalization before wrapping up this introduction section. So you see, so far, the transseries that we've been addressing, they actually arise as solutions to linear problems. So, yeah.
Sorry, I guess maybe you just already answered this, but in the previous slide, you're also considering some linear differential equation.
Yes, that's correct. So this would be a higher order linear ordinary differential equation. Yes.
If all the sigmas are independent, it's like a third order equation.
Exactly. Yeah, the number of transseries parameters would correspond to the order of the differential equation.
What psi I, is that the same perturbative series? Or
These guy, the psi-i's, you mean?
yes.
The psi-i's, they are asymptotic series, much like the first one, but they are not identical to this one. They are other asymptotic series that emerge from this discontinuity around the respective singularity. They emerge here when you compute the discontinuity encoded in this Borel summation. But they are also asymptotic series, yes. Okay, so if there are no more questions, I'll move on. Okay, so in generic nonlinear problems, the situation is more complicated, and that is because in the Borel plane now singularities don't appear in isolation. Okay, instead they belong to these towers extending all the way to infinity, such as the one that I've depicted here. And the reason for this lies in the fact that if we actually attempt to plug a transseries ansatz into a nonlinear ODE, then that contains a single non-perturbative sector multiplied by a single transmonomial, then the nonlinearity will enforce that our transseries will need more non-perturbative sectors attached to multiple powers of this transmonomial. And so if we put them in and put our ansatz back in the equation, we realize that we need more. And so iteratively, we realize that our transseries is only complete when we have a non-perturbative transseries sector for each positive integer power of the transmonomial that we started with. And so inevitably, we are led to a transseries that looks like this, okay? Where, again, we have our typical perturbative sector, so the asymptotic series we started with. But now the second term iterates over all non-perturbative transseries sectors, and now there's an infinite number of them. Okay, so here there's 2 notes that are important to make. The first is that despite having an infinite number of transseries sectors, in this case, because they lie on the same tower, they are all associated with the same transseries parameter. Okay, it's just that you raise the parameter to different powers, multiplying the different sectors. And the second remark is that precisely because in the Borel plane the singularities are all aligned, so they are all radially aligned, they will pose as a single obstruction to the analytical extension of the Borel summation, taking place in a single Stokes line. Okay, and that's what I try to convey with this picture here. Now, the novelty in this case is that the non-perturbative discontinuity is given not just by the integral of the Borel transform over one contour, but over all of them. And so it's going to be proportional to the Borel summation of not just one transseries sector, but an infinite series of them. Okay, so it's much more complicated. However, despite this added complexity, it is still possible to perform the good and unique analytical extension of the Borel summation over asymptotic series upon crossing the Stokes line by performing an appropriate transformation of the transseries parameter. In this context, this transformation, often called a connection formula, which I've denoted here by this S, takes the shape of a highly nonlinear function, precisely because our original ODE was nonlinear, but it's still true that we can fully reconstruct it from the Stokes constants that we've defined in the previous slide. Okay, so basically everything works, it's just that it's a bit more complicated. All right, so this ends my introduction to resurgence. Let me just go over some key points. So Borel summation turns asymptotic series into locally holomorphic functions, asymptotic to the original series. Borel plane singularities prevents us from going global, that is beyond Stokes lines, by posing as obstructions to the analytical extension of the summation method. Circumventing these obstructions requires complementing the original series with non-perturbative sectors, upgrading it to what we call a transseries. And finally, upon crossing Stokes lines, transseries parameters need to shift according to connection formula to ensure analyticity. Okay, so these are the key points. Let me move on to my resurgent overview of matrix models.
Can I,
yes?
This curly S map that you had on the previous slide.
This one.
Yeah, so this will in general depend on the particular differential equation you're studying.
Yes, it's highly dependent on the equation, yes.
The previous slide, you were just adding them.
Yes, because you see, when it's a linear differential equation, then that map will be a linear map. So it's literally just adding the Stokes constants. But in nonlinear equations, it takes more complicated forms. Yeah, often involving logarithms and functions like this.
But also then, you know, when you have this infinite sum on the next slide.
Yes, here.
Maybe do a Borel summation on each of them. Each small n, but how do you know that that infinite sum is convergent, or is it convergent? Like
the sum over n, I mean.
Sorry?
The sum over n. So
so let's say you apply the Borel and the inverse Borel transform to each series. So then you get
yes.
functions, but you're still summing an infinite number of functions.
Yes, that's correct. So we don't have a rigorous mathematical proof that precisely tells us the instances in which these series will converge. But so that's true. So we generally work case by case basis. In the cases that we consider, we check different different places in the perimeter space, and we test for convergence. And quite often it converges. Also because
of this function, that it exists. I mean, that's why you do Borel transform. You represent it as an integral of something which is well defined and convergent. So your sigmas appear because you don't know the contour, but once the contour goes around the singularities, the integral should be convergent. You just have to prove it by analysis, usual analysis. Not as a series, but as an integral. So the integral should define the function.
Right. But you're talking about the integral you need to solve the Borel summation, right? But the Borel summation just applies to the psi ends. You still have to look for the convergence of the series that sums over all of them. And and this is a bit more subtle, but typically because they're exponentially suppressed, this works well.
But ultimately, aren't you supposed to represent the whole function as a maybe multiple integral, multiple version of Borel integrals, or single Borel integral?
Well, yes. So the whole function should be represented by a summation over a lot of Borel integrals, if you want. Yeah, because we apply the Borel summation for each psi m. So each psi m will have a representation as a Borel integral.
So the whole thing should be an integral, maybe some period or some integral over.
Ah, yes. I think I assumed
cycle in the high dimensional space. The question is whether the integrand is finite.
Yes. So you are exploiting the linearity of the integral over the integration domain to absorb this summation in the cycle somehow. Is that correct?
Can I also ask a related question? That is it known that in nonlinear problems we still get a Gevrey one kind of series which can be Borel resummed?
Yes. Yes. In all nonlinear problems that we've tackled so far, it's always true that the series are Gevrey one. Yeah, we have never found not a Gevrey one series.
I see.
Yes. Okay, so if there are no more questions, I'm going to go on to my research and overview of matrix models. So I'll be brief here. So the physical setting will be that of a generic Hermitian one matrix model, like the one that I've written here, where V stands for the potential, which we take to be a generic complex polynomial. GS, highlighted here in purple, is the matrix model coupling constant. And the curly L, sitting on the integral domain, you can take it to be the set of size n square matrices that are diagonalizable under a unitary transformation into a diagonal matrix whose eigenvalues lie on these one-dimensional submanifolds of the complex plane called Lefschetz symbols. Okay, so the Lefschetz symbols, they are defined to ensure convergence of the integral, and so their shape is highly dependent on the choice of the potential as well as on the phase of the matrix model coupling constant. And in a particular instance in which the Lefschetz symbol aligns itself with the real line, we say that the matrix model is the Hermitian in the strict sense. But in the more generic case, we say that the matrix model is normal. Now, this is a very small detail, but in what follows, we'll tackle the generic case, so not just the strict Hermitian case. So these matrix models have
this
yeah.
L, you are deciding just based on the function V of a single variable.
Can you repeat the initial part of the question? I couldn't hear, sorry.
V is a function of a single variable, right? V of x.
Yeah. It's typically you take it a polynomial. Typically.
It's a polynomial, and then this L is just determined by that single variable function.
Yes, it's going to be determined by that polynomial as well as the phase of the matrix model coupling.
Eigenvalues you distribute at different critical points of V. They have different symbols for different types of critical points of the matrix.
Okay.
Yes. I'll be a bit more precise what I mean by Lefschetz symbols later on. So I'll go back to this. So there's two physical limits that are of interest. The first one is the so-called large L limit or 't Hooft limit, and as the name suggests, this is the limit in which we send the size to infinity, the coupling to 0, and we keep their product, called the 't Hooft coupling constant fixed, which I've denoted here by T. And it's interesting because it produces models that are dual to certain subclasses of B-model topological string theory. And the second limit of physical interest is the so-called double scaling limit that one obtains by zooming in on the edge of the eigenvalue distribution of a large N matrix model. Okay, and it's very useful for physics because it produces models that are dual to theories such as minimal string theories or even jerky gravity. So I should mention that in what follows, the exact construction that I'll provide applies equally well to both cases. Okay. All right, but so the first step in solving the matrix model consists in diagonalizing it. And if we do this, we are going to obtain this expression here, where this delta stands for the van der Moon determinant, and this curly C sitting on the eigenvalue integration domain is precisely the Lefschetz symbol that I was talking about before. So you can really think of it as the eigenvalue integration domain, which indeed it's a one-dimensional submanifold that emanates from critical points of the potential and then it goes off to infinity. And what the right-hand side of this equation is telling us is that all of these complicated-looking integrals eventually culminate in a rather simple product of coefficients, which I highlighted here in purple, that turn out to be simply the norm of a set of polynomials, which I've highlighted in green, that are orthogonal with respect to the inner product that I've defined on the left-hand side of this equation. And for this very reason, they are called orthogonal polynomials.
Sorry, question. So
Yes.
seems like you are assuming that the contours of integration over individual eigenvalues are all the same, but they don't have.
Yes. So for now, I am assuming that. I realize that there is freedom in choosing the critical point from which the contours can emanate, but I'll be more specific on this. So basically, I want to tackle a large n matrix model. And because of this, I'm assuming that all of the left shade symbols that you see here, they are associated with eigenvalues that take place on the eigenvalue distribution, on the cut. That's my definition for them. So, okay. Right, so orthogonal polynomials, they are very useful because one can compute them recursively by resorting to this equation, which for the purpose of this presentation, it's not very important to tell you what Sn and Rn are. What is important is that indeed, we can use this equation to compute enough orthogonal polynomials to use the first equation in order to solve for the matrix model exactly for finite values of n. But now you can rightfully ask, what happens to the limits that we are interested in? And indeed, if we take the large n limit, or the Toth limit, then after some algebraic manipulation, we can extract from this a finite difference equation whose solution somehow captures the behavior of large n of these coefficients, Rn. And indeed, solving this equation, which is often called the string equation, really does amount to exactly solving the matrix model. Okay, and so this equation is a very powerful one, and it takes a very central role in the theory of large n matrix models. If we further wish to double scale our matrix model, we can do so, and our finite difference equation turns into an ordinary differential equation, or more precisely, into an element of the integrable KdV hierarchy, and the associated model is then called a multi-critical model. So I will have more to say about these models towards the end of the talk. Now, the important feature here is that we finally have obtained an equation, namely our string equation, and so we can actually attempt to build a transseries representation of its solutions in the hopes of obtaining a good non-perturbative completion of the matrix model. And we can do this simply by plugging a transseries in the string equation and solving for its coefficients recursively. Okay. So if we do this for the cubic matrix model, which, by the way, it's just the Hermitian one matrix model whose polynomial is a cubic potential, then we are led to the two-parameter transseries that I've written here, where sigma 1 and sigma 2 denote the transseries parameters. And as you can see, we have an infinite number of transseries sectors labeled here by n and m. And the reason why we have an infinite number of them is precisely because the cubic matrix model string equation is highly nonlinear. Upon closer examination of the Borel transform of the pattern,
Either our internet or